All right, well, thank you all for joining us for our third webinar, and today's topic is on phenomenon, and Scott King is going to do our presentation for us today. So Scott, I'm going to go ahead and let you take over.
All right. So I have a little Google slideshow just to kind of walk through, and I've got a little background of what phenomenon are, and then some example phenomenon that we can talk about. And please jump in. Ask questions, share examples, whatever. Let's see here. Did that work? Can you guys see that?
Yep.
All right. I don't know if I can present. Does that still work? Does that work? All right. Part of this comes from the framework for K-12 science education, a study and a lot of research that was done on how to teach in the K-12 schools. Nebraska is in the process of getting new science standards, which are framework inspired. And so the phenomenon are part of this whole framework process, and it focuses on the process of doing science. How do we get kids to actually do science and not just learn about discrete facts? And we do have some, as part of NATS, some columns that are coming out, some articles in the next couple weeks. So if anybody's interested, those will be on the NATS website, and I'm sure we'll be advertising those Facebook and Twitter and stuff like that. So the process of doing science, there's three main parts, which are the disciplinary core ideas, or the standards and ideas to be taught, the science engineering practices, the how we teach, and the cross-cutting connections, which is how one science concept relates to other areas of science. And what ties all of these together is the phenomenon, which is what we're talking about today. The phenomenon provides the why. But Mr. King, why do I have to learn about this? When am I ever going to use this in my life? And that's kind of where this is at. They are observable events that we use our science knowledge to explain, and they require engineering solutions to problems. So it gets both of the science and engineering components tied in there. And it shifts the learning from learning about a topic to figuring out why. One example I heard was that you walk up to kids and ask, what are you learning about today in science? Instead of saying, I'm learning about mitosis and how cells divide, we'll be discussing cancer and how cancer spreads and kills people. It's the why component of it instead of just some random discrete topic. Good phenomenon will be specific events. You're not looking at broad scale, how did the earth form, but a specific feature within that. They're going to build on our everyday experiences, and they're going to be observable to students. Observation is open to interpretation here, whether it be demonstrations, labs, videos, analyzing data using tools like microscopes or telescopes. They're going to apply multiple performance expectations or standards. They're not just one discrete standard, but they're probably going to cover a wide variety. And especially for upper levels, they need to be too complex to solve, and they're not Googleable. It's a big good word there. But if I go to Google and I ask, how does something happen? It's complex. I don't want to be able to find an answer in 5 seconds, because then kids aren't learning. They figure out they can Google it and they're done. Try to find something that is a little bit more engaging and harder to answer than straight up. Now, younger grades, of course, that's not as big of an issue. So using a phenomenon, they should engage in a science and engineering practice, and it's not just a phenomenon by itself or an individual event, but it's also the student-generated questions and the learning that comes from that. So the parts of a phenomenon start with an anchor event, which is the phenomenon itself, and then the developing of underlying explanation, or what they call the gapless storyline. And a phenomenon should take a unit, a week, 2 weeks, 4 weeks, however long your unit is, to fully explain. So again, it shouldn't be so simple that it's answered in a class period, but it should engage a large portion of learning. And So here's a good example. This one we got from a workshop this summer at Lynx. The anchor was that this author of the workshop, the book that we had, says that trees were collected, some aspen trees, at 9,000 feet and at 6,000 feet. He went up in the mountain, collected some trees, and brought them down to his house at 5,000 feet. But he noticed that they leafed out at different times of the year. They budded their leaves and developed them at different times. And he asked the question, why? So that's our anchor. This is the thing that's going to hook the kids. But this is open to a lot of areas that you can study. And if you look at my performance expectations or my standards, we can talk about genetics, we can talk about ecology, species competition, plant biology. In this particular example, when I went online and I tried to Google the answer, I found out that aspen trees have both male and female types, and I didn't know that. And they leaf out at different times. So here you get some plant biology related things. But everybody knows that aspen, of course, are genetically linked through their root system, and that the real reason had a lot more to do with species competition, that when they had a chance to leaf out, they were able to outcrowd other species, before they got crowded out themselves. But you wouldn't answer this in one class period. I wouldn't give everybody the answer to this question. My next day, after the kids generated some questions and some possible experiments, we would be going into our lessons talking about what it is I wanted to focus on as a teacher. Are we studying genetics? Are we studying species competition? Are we studying plant biology? And let kids explore a little bit. I'd give some lessons along the way and let them assimilate that information I gave them into their answer. And then they would develop their full, rich explanation to this phenomenon at the end of the unit. So here's one that I do have a more complete explanation for. We all know that in the summertime, June, July, it's hot. But we are the farthest away from the sun during those months, during the summer months. And we are closer to the sun during the winter months. So why is winter so cold when we're so close to the sun? That's counterintuitive. So you can use a discrepant event as a phenomenon. So we can talk about the seasons. If you're having like little kids, what are the differences in the seasons? Energy concentration, waves, the inverse square law if you're in physics. You can talk about differences in hemispheres that, of course, the northern hemisphere is in summer when the southern is in winter, and vice versa, again, for little kids. And you have them develop their explanation. And a weak explanation would be something just simply this. The earth is tilted and different parts get different amounts of sunlight. That doesn't show real learning about the topic. That's what basic information could they regurgitate out of, an entire lesson. And we tend to let kids get off the hook with an answer like this because they gave a right answer, but it wasn't detailed. It wasn't fully fleshed out. So in this case, there's no storyline that links all the events together or mechanisms for why does the sunlight have more during different times of the year. A better example, and this is by no means complete, and I'll share the link to this particular one later on. The Earth revolves around the sun, and it's in the ecliptic, and it takes 1 year to go around. It also rotates on its axis, blah, blah, blah. Basically, you're going to build up all of the evidence, all of the details for why is it that we have more sunlight. The Earth is pointing in a certain way. What kind of wavelengths make it through the atmosphere? So visible and radio waves make it through the atmosphere. Down here at the bottom, they have a thing about the flashlight. So this would have been one of the investigations that kids may have done along the ways they were learning about this particular phenomenon. That maybe you asked them to show a flashlight on the floor and circle it with a pencil on a piece of paper, and then they spread it out at an angle, 30 degrees, 45 degrees. And ask them to circle that, and then they can measure the concentration of the rays or whatever. And this just continues, and I didn't write it all down. But you can see how you have the anchor, you had all these lessons about different things, and then you ask them to come up with the explanation at the end. And then their explanation needs to be a detailed, full written explanation. This is one that I love that I came up with, which is the piping plover. Of course, I live near Lake Mac. And every year they section off whole sections of the beach for this bird and the least turn. And I've had a lot of people ask me, the lake's only been there for 75 years. This bird's been around a lot longer. Why on earth are we sectioning off Great Beach for this stupid bird? Why doesn't he just go to his other nesting habitat? And a lot of people don't know this, and I really didn't know this until just this past year, the whole story. And so I have my anchor, which is this whole bird thing, some performance expectations that I can do, the ecology, I can talk about niche and habitat, man's impact on the environment, Earth's history, and I can write my explanation after I learn all these different things. And a lot of this has to do with, if you remember, they talked about the Platte River being an inch deep and a mile wide when the settlers came across the country. Well, it's not a mile wide anymore. It's because we've controlled it through dams, and we've controlled the river channel because of our cities and things and our farming, so that we don't get that inch deep and a mile wide. So all that, when it flooded seasonally, it stripped away the vegetation in the river channel, where we now have our cities like Kearney, Ogallala, etc. And there's no place for the birds to nest anymore. Which then you can also tie this into, if you want to, like the sandhill cranes, they need shallow water and sandbars for nesting and for safety, because they listen to predators coming through the water. We can talk about the formation of the sandhills. Why does it pretty much stop at the Platte River? Why doesn't it really go south of the Platte River? Well, when sand gets into the river, it gets shoved downstream. In a class I took, the geology road trip with University of Nebraska-Lincoln, and David Harwood, he had to stop and go, okay, how old are all the trees? Well, they're all 75 years old. Why? Well, once we dam the river, trees could start growing again. So all the trees along the river are only 75 years old or younger. So you can bring in all these different ideas on how to tackle this one main thought.
Wow.
Going to chemistry, you can have, this is a lower level expectation here that if you mix two chemicals, what do you notice? Do they change color? Do they change temperature, whatever? You can start talking about the difference between elements and molecules, chemical reactions. Higher levels could talk about atomic parts and waves, different types of chemical bonds. Static electricity, again, a lower level one maybe, but you could extend this into higher level grades. If you stick the comb in the water, why does the water move toward the comb? And these are just examples of phenomenon that can start an investigation. You get kids thinking, and then you have to fill in the details later without answering this question directly. Let the kids piece together the information until they get to the knowledge for themselves. Let's see here. That's not what I wanted. We are going to exit this. How do I stop share? There we go. Boom. So that's the presentation I had. I'm going to put this on the NAT's website.
Oh.
Yeah. Mary Kay, I see that. Yeah, there'll be a presentation. The link will go onto the website. And then I also have, if you go on to the NAT's website, let's see, did I bring it up? I did. Let me share this again real quick. If you, we'll put under here the PLN resources. And then over here on the side, if you go to the Nebraska Academy of Sciences page, NGSS resources. NGSS is aligned with the framework, so it's easiest to search for some of that. There's a list here of some phenomenon-related links. And this last one here, planning for engagement, is the one that I got the solar system example from. If I scroll down here, here's the solar system example, and here's their longer explanation that just keeps going and going and going and going. They also have some really great examples of some other phenomenon and the story model and all that in here as well. But there's 3 other links here of some really great phenomenon resources. Okay, maybe that was a little quicker than I expected. Do you guys have any questions about phenomenon or about implementing in your classroom? I guess I kind of went quick.
All right, Scott. So I always get a little overwhelmed when I start thinking about a phenomenon and I go too big almost. So how would you start with it? If you were and I were just having a conversation about a topic, how would you go about, what would be kind of your steps to guide you through it?
Okay. Uh, think about what the learning objective is you want for your students. Are we talking about genetics? Are we talking about chemistry, ecology? What is the specific idea you're trying to get across to your students? So where in your unit are you? Find an example that relates to that unit idea. So if I'm doing genetics, I'll go to the aspen tree one for an example. I want to talk about not so much genetics, but maybe in that one case it was more of a species competition is really what it came down to. I'm going to do, in the case of the aspen trees, what it was is the trees at lower elevations, it's warmer at lower elevations, so a lot of other plants will leaf out quickly. So those trees have to leaf out early on, and that's that 6,000 feet, they leafed out like in April. The ones at 9,000 feet is still frozen later in the year, so they didn't need to leaf out as early, so they leafed out in May. Well, the trees that they collected were all genetic identical from each of the different elevations. But you can talk about that species competition in a way there that, okay, I want to talk about habitat and niche, competition. This is my example I'm going to come up with is aspen trees. In my class, what I had done one time actually was I put cards in a bunch of envelopes, and the person who had the right card got extra credit points at the end of the class period. So they attacked each other, and you could see them gang up on each other, and you could see them do different strategies. And then I filmed them as they were doing this and replayed it for them, and they were able to look at the different strategies they used. It doesn't matter what the phenomenon you're going to pick is. Just pick something that based on the learning objective you have. But make it specific. Don't do species competition as a generic. That's too broad. If you like caterpillars and butterflies, pick something along those lines. And this is what's great about this is it can still be very specific to the individual teacher. Whatever it is that you like to know or that you do. There's a couple of resources like on the NATS or on the NATS website. There's one which is it's like ngssphenomenon.org or .com or something like that, which they have a bunch they've already pre-built. You can kind of search through and see what you like. But it needs to be something specific. And then again, hopefully it's, especially for upper grades, not Googleable, at least not easily. And that's the trick is how do you find something that's complex enough without being, when I'm looking at it as a teacher, when I first started looking at these, how am I supposed to come up with these if I can't Google? Right? So we need to work better at coming up with a list of phenomenon. And there's actually, I don't have that Twitter handle. I sent it to you and Sarah a while back. That is another website that has phenomenon that are out there all the time that, they're publishing more and some good ideas to search through and find ideas.
All right, I'll find that Twitter and post it too. So, any other questions? So, what you're saying, Scott, is this is something that I've kind of been doing all along and just didn't realize it.
The trick though is not just having a phenomenon, but leaving it out there for the entire unit that you are actively finding information or you're teaching information for kids to bring back together. And at the very end, they have to write up that storyline, that explanation of why did that happen. But it's applicable then to other areas as well. So if I take the piping plover one, that explanation of the Platte River can also be applied into the sandhill cranes or whatever else. You don't just leave it hanging as one very specific example. It's supposed to be cross-cutting and see that larger view.
So do you go ahead and assess these like into the unit projects, or is that
Yeah.
how you used it a little bit?
Um, Absolutely. You could make it part of your, instead of to supplement a test, if you're going to write just a knowledge test, their ability just to write, an essay essentially, or a project, a brochure, poster, whatever it is, however you want to assess this, could be to, okay, here was our phenomenon, share it, refine it. But a lot of times what you're going to probably do is have groups, you work together to help spur ideas. So here's my phenomenon. Small groups around the room will process this information. You share it with everybody in that group or the room. You critique the ideas. You may pull out a couple of things that you want to follow as paths. So on the aspen trees, maybe one group wants to follow about sexing trees, the other one wants to follow about genetics, and you kind of follow a couple of different pathways and share ideas. And when one gets removed from possibility, then you're left with another explanation. And toward the end, everybody should have the same information. I mean, just like any other class, it should all have the exact same information, just being able to explain it to a teacher.
So it's a little bit of differentiated instruction where they can kind of choose the path, but then in the end they come up to the same ending line, so to speak.
Somewhat, yeah. I mean, you're still going to have your lectures and you're still going to have your labs and your worksheets that you go along in there, but it's how do you apply those learnings, those lessons to this other idea. It's not just discrete facts, it's applied.
Okay, cool. Anybody else have any questions, comments?
I have some other resources and I test and for determining whether it's a DCI or a phenomenon. So I'm sure that I get those to you. You might have to send me a reminder. Like,
We can do that.
I guess I didn't get to catch that.
I think it was about DCI and phenomena. Sarah?
can you guys hear me now?
Yeah.
So I have some tools that you can use. One of them is really short. It's called a phenomenon yes test. So it's kind of a checklist. Is being able to distinguish between a DCI or an engaging phenomenon. So tools that you post.
Okay. The phenomenon yes test would be kind of neat to look at, absolutely.
I wanted to say thank you. I'm making me think of new things, and that's wonderful. Thank you for doing this.
Well, I thank you for joining us. Appreciate it. Sorry I was kind of late. It was a crazy day. So, and if I don't put things in my reminder calendar, then I forget. So thank you guys for sticking around.
Yeah.
Anything else, Scott?
Don't be afraid. Just try it. 1 or 2 lessons, work with it. You don't have to change too much to incorporate some phenomenon. It's that hook that hooks them through the entire unit you're about to teach.
Okay. All right. I'm planning a new unit for my 7th grader, so we'll give it a try. Genetics, ironically.
All right.
Yeah.
You'll have to tell us how it goes next week or next month.
Yeah. I might have to do some consulting. You're available via email, right?
Yeah.
Good.
And Mary Kay as well. If you need anything, feel free to email and Nats or myself, and we'll just get it figured out. And
all right. Okay, sounds good. I think that's it, unless you guys have anything else. All right. Thank you.
that's it.